how do we go about solving this equation? Well, the first thing that we're going to do is look at it and think. dx dt equals a times x. Let's simplify and say that a is equal to 1. We're looking for a function whose derivative is itself. You and I both know an excellent solution. That is, x of t is e to the t. Now, what happens when we put the a back in there? Well, if we just think about it a little bit more, we see that putting an a up in the exponent gives us, as its derivative, e to the at times a. That is what we're looking for. We could, of course, put an arbitrary constant, c, out in front, and you may check that this is a solution to that differential equation. What is that constant? Well, we might, following our previous example, call it x naught, the initial condition, what you get at time 0. This method of solution is sometimes called solution by Ansatz, which is a fancy word for saying we took a guess and it turned out to be correct. There is, of course, a more principled approach. One such approach is based on series, where we assume that our function x has a series expansion, c0 plus c1t plus c2 t squared, etc. These constants, c sub k, are, to us, unknown. Now, what are we going to do with this? Well, the differential equation tells us something about the derivative of x with respect to t. We can differentiate the terms of this series very easily. What the differential equation tells us is that this is equal to a times x, which of course is a times c0 plus a times c1t plus a times c2t squared, etc. Now, here is the important step. If we have two series that are equal, then their coefficients in front of the various terms must also be equal. And now we can work one step at a time. The constant terms, equating them, tell us that c1 is equal to a times c0. Well, that's good. If we knew c0, we would know c1. What does the next equation, that of the first order coefficients, tell us? Well, it tells us that c2 is equal to 1/2 a times c1. But we already know what c1 is. c1 is a times c0. So that tells us that c2 is actually 1/2 a squared times c0. What happens when we take the coefficients of the quadratic term and set them equal to each other? Well, 3 times c3 equals a times c2. That means c3 is 1/3 a c2. Using what we know about c2, we get 1 over 3 factorial times a cubed c naught. I'm going to let you keep going with this and see if you can find a pattern. That pattern, through the method of induction, can show that c sub k is 1 over k times a times c sub k minus 1. And that is 1 over k factorial a to the k times c naught. That means when we look at our original series, x of t, it's the sum over k of ck t to the k, that is c0 times 1 over k factorial times a to the k times t to the k. Now, I'll let you verify that that is really c naught times the exponential function e to the at. We obtain our solution, which we already knew was true, but from a more principled series approach. That, however, is a little complicated, and so we are led to our last and best method of solution, that of integration. Beginning with x as a function of t, we differentiate using the chain rule to obtain dx is dx dt times dt. Now we know something about dx dt since this is a solution to the differential equation. It is a times x. And now we're going to use the method of separation, which means we move all of the x terms over to one side of the equation, and we keep the t terms over to the other side. This gives us dx over x equals a dt. And now, using the fact that the integral is an operator, we're going to apply it to both sides of this equation, obtaining the integral of dx over x equals the integral of a dt. What is the integral of dx over x? Well, it's the antiderivative, natural log of x. What is the integral of a constant times dt? It's simply at plus an integration constant. Now, to solve for x, we apply the exponentiation operator. E to the log of x is simply x. On the right-hand side, we get e to the at plus a constant. Splitting that up into a product, we obtain a new constant, we'll call that c as well, times e to the at. That is our solution, and it was obtained effortlessly. One of the things that you'll notice is that e keeps coming up. It is not a coincidence that e to the t appears as the solution to the simple ODE, dx dt equals x, or as the series, sum of t to the k over k factorial, or as the indefinite integral, as we just saw. In all three cases, you can interpret the constant of integration as an initial condition, or the constant term in a series, or the arbitrary constant of integration. And so the question of why the plus c has many answers.
And so we see that three of the main characters in our story cross paths: integration, series, and solutions to differential equations. In our next 3 lessons, we're going to focus on one of these characters, solutions to differential equations, and see how integration helps us to compute and understand them.